Hello class, this is a lecture on chapter 15, Computed Radiography. I've split up 15 and 16 out of your Bouchon book, so this lecture will be very quick and to the point, as will the next one on chapter 16. Okay, so computed radiography. Computed radiography is a subset of digital radiography, so they're both linked, they're interlinked. Okay, digital radiography was introduced in 1981 by Fuji with the first CR system. Okay, CR is the most widely used of the DR modalities, and there's always going to be a need for it. This is just a review of the workload steps used in screen film radiography, just to give you a foundation on where it came from and why CR is an improvement. Okay, so the main thing here is these are all regular workload steps of processing a patient from ordering the exam all the way out to escorting them out and done with the exam. But back in the day when screen film was still around, we had to load cassettes, we had to perform exams, we had to process the film, sometimes with chemicals in dark rooms. Then we had to reload the cassettes, we had to hang those films to QC them, see if we needed a repeat, etc., etc. Okay, so there was an extra step there. Okay, CR will eliminate some of the steps and can produce better images at a lower dose. And that's just a recap of what CR has brought to the radiography department. Okay, there's important terms that you need to know in this chapter, so you will be tested on these, so make sure that you know these terms. Imaging plate, and the abbreviations are next to them. So IP is imaging plate, PD is a photodiode, PMT is the photomultiplier tube. PSL, photostimulable luminescence. Okay, PSP is photostimulable phosphor. SP is storage phosphor, and SPS is storage phosphor screen. Okay, image receptors. This slide is comparing screen film and computed radiography cassettes. Okay. Screen film uses an image receptor, which was an X-ray sensitive plate encased in a protective cassette. Computed radiography, same thing, an X-ray sensitive plate encased in a protective cassette. Okay, both of these produce a latent image that is made visible with processing. Okay, but that's where the similarities stop. Okay, with screen film, that uses a scintillator that emits light in response to an X-ray interaction. And since you had a piece of film next to it, when that light was emitted, it burned onto the piece of film. So when you process that with the chemicals, you could see a radiograph. In CR, in response to X-ray interaction, there is, and we're going to talk about what this substance is, a substance inside that cassette that has certain electrons in its outer shells that get full of energy, okay? And in these trapped electrons are in a higher energy metastable state, okay? And here is a look at that interaction. So the X-ray interaction with the PSP, the photostimulable phosphor, that's inside your cassette. Once the X-ray energy is absorbed, it makes that electron in a metastable state. Now, sometimes right away the light is emitted, 50% of those electrons, the light's emitted right away, but the other 50%, those electrons hang on to that energy. So the light is not released yet, it's just hung on there. And these 50% that are left are the ones when we put them into the CR reader that the mechanics and the electronics inside get rid of that stored energy in these electrons that are hanging on to it, and they emit light when we want them to, and the light is detected and sent to a computer and digitized. And so that's how CR images are made. So we're going to get more into that. Okay, PSL, photostimulable luminescence. Okay, the substance that we use inside of our cassettes when we use a CR is barium fluorohalide with europium. Okay, This substance emits it takes that energy from the X-ray and holds onto it, and some of the electrons, like I said, 50%, emit the light right away, promptly. But it also, the other 50% holds onto it. And when we expose those to a different light source under our control, like in the CR reader, then it will emit light again, and we can control that and detect it. Okay, the process of holding on to that energy and emitting that light later with a different light source is called photostimulable luminescence. Okay, the europium is an activator. So without the europium, there would be no latent image. We wouldn't be able to form an image. Okay, so the PSL, this photostimulable luminescence, is what happens when a cassette is processed and exposed to this intense laser light, and that's how we control the second round of light being emitted. Okay, here's a picture of a PSP, and it shows the layer. Okay, the PSP, the phosphor, is inside this layer. It can be in crystal or powder form. It can also be in some lines, which I'll show you next. It's grown in a linear form. Okay. Notice that on the bottom there is a lead layer that prevents scatter. Okay. And if it's in the powder form, there's a binder that holds it in this layer, in the emulsion. Okay, here's the other one. It's called needle PSP, and it's just lines that they have grown. Okay, because the latent image occurs in the form of metastable electrons, these screens are called storage phosphor screens, or SPS. It appears white because these small phosphorus particles scatter light. In the top one, they are scattered throughout via a binder, and it's mechanically stable. Okay. Some are in this powder form, and then others are phosphors grown as linear filaments. Okay, and that's called needle PSP. Okay, the imaging plate. The PSP, either in the binder, the powder form, or in the linear phosphors, is housed in a rugged cassette called an imaging plate, IP, imaging plate. This is one of the principal advantages of CR. It can be substituted for screen film cassettes and used with an existing X-ray system in an imaging room. So say they have an old, antiquated X-ray room, but the tube and the table and everything are still good, but they want to upgrade to digital. They can do that with the existing tube in their existing room and just change out the cassettes for digital cassettes and a CR reader. Okay, so that's one of the principal advantages. Another advantage is, besides, is no dark room. You don't need any chemicals. And additionally, like I said, the IP has that lead backing, which reduces the back scatter. Sorry, there's a typo right there. Reducing the back scatter, which improves contrast resolution. Okay, so we're going to get into how the image is processed. Okay. So exposure, number one, you expose the cassette. Okay, you've taken an X-ray. So what's happening inside the cassette is the excitation of all those electrons into this metastable state. Now, like I've said over and over again, so that'll be a test question, 50% will emit their light immediately or promptly. Okay, the other return to their ground state over time. Okay. And it's so therefore, since 50% have already emitted their light and the other ones are going to emit their light, okay, either by us directly making them do that or over time, it's important to process those cassettes as soon as possible after the exposure, because otherwise that latent image will begin to fade. Okay. So this slide just shows you there's 4 different steps, and the first one is to expose. All of those X-rays go in, they stimulate that phosphor in our layer of phosphorus, and those electrons hold on to that energy. Okay, stimulation is the second step. And how we do the stimulation process is, like I said, half of the electrons have already gone to their ground state and they've emitted light. The other half have held on to it. Now we're going to make them emit that light. Okay, so what we do is we stimulate them with a laser. And we're not going to get into the physics of what wavelength the light has to be to get them to emit the light, but it's in a different color and all of this kind of stuff. So, but anyway, the laser will stimulate the phosphorus that is held on to the energy. They're still in the metastable state. It will stimulate them to release or emit that light, okay? And consequently, as the laser beam intensity increases, so does the intensity of the emitted light, the signal, okay? So next, you need to take that emitted light and do something with it, and that's called read. Okay, this step is detecting the stimulated emission, which we have made happen with the laser. And this light is detected by photodiodes. And these are the part of the computer processing system. Okay, so they're going to detect the light. This information is then collected and digitized to produce an image. Okay, that's the read step. Okay, the fourth step in the process doesn't necessarily have anything to do with how the image is processed. However, if you look at it in a different point of view, yes, it does, because you have to erase the PSP. And the reason for that is the stimulation cycle does not completely transition all the rest of the metastable electrons, okay? And if a latent image remains on that PSP and you take another radiograph with that cassette, you could get ghosting on the next image. Okay, so what you have to do is you have to remove any residual. And this is done by flooding that entire screen with a very intense white light. Okay, and that fourth step is called erase. Okay, so then we're going to talk about the CR reader. Okay, and how the cassette is actually processed. Okay, we know what happens and how it retains energy to make a latent image and how we get that energy out of the phosphor, but this is how the cassette is actually processed mechanically. Okay, once the IR is placed into your CR reader, the IP, that imaging plate, is removed and fitted to a drive mechanism. Okay. It moves the IP very slowly, but very consistently. It has to be consistent or you're going to get some kind of artifact or wrong translation of the image. So it's got to be perfectly consistent. And when this is happening, this drive mechanism moving the IP slowly, this is termed a slow scan. And at the same time this slow scan is happening on the long axis of the IP, this deflection device is deflecting a laser beam back and forth across the IP. And this is termed fast scan. So, and the laser is focused by these lenses, the oscillating mirror or the polygon mirrors. They're focused by this lens system to keep the laser beam diameter small. And this is very important for high spatial resolution because apparently the physics of laser beams increase. So this way it keeps it small. Okay, so this is critical for ensuring high spatial resolution. You need to remember that. Okay, two things to note here is the IP, the imaging plate, barely leaves the cassette during the process. Okay, therefore it's not subject to roller damage. Okay, also the scan is done at right angles. The scan from the laser beam is done at right angles to the direction of the grid lines. So aliasing artifacts are very minimized. Okay, so those are a couple of advantages to this CR system. Okay. Once the PSP is stimulated and the light is emitted and we're ready to collect it with those photodiodes, we filter it right before we collect it. And it shows that right here, this optical filter. Okay, we filter the light right before we collect it because the stimulating light is noise at this point. We don't want those waves of light to be detected by the photodiode to be part of our image. That wasn't anything to do with the X-ray. That stimulating light cannot be mistaken as part of the latent image that we're producing. Okay, I hope this is making sense. We only want the emitted light coming off the phosphorus to go to the photodiode for our image. Okay, so in this case, emitted light is the signal that we're looking for, and stimulating light is the noise. Okay, so proper filtering is very important, and this will improve our signal to noise ratio, okay, with proper filtering. And you'll note too that if you don't have proper filtering or something's awry in your QC on your CR reader, you can see some wavy lines on your images and things like that that clue in the engineers that that part of your computer system is out of whack. It's out of specs. Okay. Okay, image characteristics. So once you've developed your image and you have a radiograph to look at, you're still looking for spatial resolution, contrast resolution, decreased noise, okay? And how they measure those things, so remember back, we have already learned about the characteristics curve. Well, that was for that S-shaped curve with the toe and the shoulder. That was for screen film. Now we're looking at the same kind of curve idea, but for CR. And it's not called a characteristic curve when we're talking about CR. Now it's called an image receptor response, okay? And you'll notice that it's a straight line. So all you have to know is it's a straight line versus the characteristic S-shaped curve that you learned about. It still has the same optical density on the y-axis and your exposure range on the x-axis, okay? But you do note that your shades of gray with your screen film, you'll have 30 shades of gray about that you could see with your eye on a film hung up on a alternator. But with CR, you have about 100,000 shades of gray. So you have an extremely wide latitude of desirable images in the optical density range, okay? And it's going to be represented here for you. Okay, so screen film, these are examples of screen film here on the left side of the screen in these pictures. This just shows a radiograph done with screen film technique where the technique has to be right on or you're going to have an image that's too light or too dark. Okay, but in computed radiography, you can show that you can use different techniques, but look at how similar the pictures still can look. Okay, so the latitude is a lot wider, so we have a lot more shades of gray that are acceptable to the naked eye and have in decent images. Okay, now this doesn't go to show that these are okay. 80 mass on an E, really, for your patient dose, that's going to be outrageous. Okay, but it shows that you could still get a decent image with a computed radiography. If you had shot that with screen film, it would be black, okay? Okay, so image noise, that can still happen in CR, okay? The principal source is still scatter radiation, no matter if you're using screen film or CR, okay? Sources of noise in screen film, though, are the quantum model, X-ray quanta absorbed, that's just meaning the extra X-rays that are absorbed, scatter radiation, latent image fading. So that can still, if you're not processing your cassettes well, still in the screen film work, you can still fade the image because there's still light being produced in those, okay? Image receptor noise, phosphor structure, phosphor particle size distribution, overcoat reflection layers, etc. Okay? Sources of noise in CR are the mechanical defects like slow scan driver, fast scan driver, the laser intensity control, the scatter of the stimulating beam. So all of those things can produce noise in CR. In addition, sources of noise in computed radiography are all of the ones that we had in screen film as well. Okay, so computed radiography is much more sensitive, and as a result, all of these things can mess up your image with CR. okay? But in conclusion, even though all of those things can mess up your image in CR, you have a lot more control, okay, over it. So the biggest advantage in CR is your image contrast is constant. So images can be made at a high KVP and a lower mass. You still have a decent image, which results in reduced patient doses, okay? Also, fewer repeat exams needed due to that wide latitude, okay? And there is no need to deal with reloading film cassettes or maintaining chemicals, all of which can mess up images if they're not done correctly, okay? And if you'll notice, there's one less step here in this workload, okay? One less step, which is better than none, I guess, all right? So we'll talk about Chapter 16 in the next lecture.